Hello everyone, welcome to my channel. So today we are going to start a new subject which is called Introduction to Nanomaterials. So Introduction to Nanotechnology. Under that module 1 we are having the, I guess previous video we discussed about a brief introduction we gave regarding the syllabus and how exactly the COs and POs have been arranged. All those things we discussed in the previous class. So in today's class we will start the module 1 of the subject Introduction to Nanomaterials. This particular subject is there for first year students of VTU. Not only VTU, there are a lot of universities I have made this subject as a mandatory subject for first year students. If you see my previous video, you will come to know that why this particular subject has been is a need of an hour, because this particular subject nanotechnology is not restricted to a particular field or a particular branch. Okay, so you take for example the various the core branches like maybe civil engineering, mechanical engineering, or computer science, E&C, or electrical, or any biological sciences. So if you are talking about all these things specifically, then after this core, through the core branches, again we are having many other sub branches. Like for mechanical engineering we are having the material science, advanced materials, all other stuff, or and we for electronics we are having telecommunication, cyber security, IoT, blockchain technology and all. And for CS we are having AI/ML, computer science and design and other stuff. And when you come back to the other part of this thing side, like a biological sciences, we are having biotechnology, biomedical field, textile engineering, environmental engineering, all other stuffs, right? So if you are considering all of these this thing, even in civil engineering, construction, structural engineering, all other stuffs. So if you are considering all these particular fields, and one particular common application, like a particular common application you can find is that by using nanotechnology. And you might ask how come the nanotechnology can be so important so that it can be applied for all the fields. So the reason is very simple. So since the nanomaterials, the materials, whatever we see, as I imagine this is a bulk material. Now I have to reduce it. This is in the size of some 10 centimeter or something like that. So now I want to reduce this particular material into the nanoscale. So I am not reducing whole this thing as a jadoo like a nano. So I am cutting this particular thing into half. So I am getting 5 centimeter. Then again half and half. So I am getting 2.5 centimeter each block. So like that, every block in this particular structure has to be nanoscale in structure. Okay, so that is like almost 1 billionth of meter. What is nanoscale? It's 10 to the power minus 9 meter. So when you say 10 to the power minus 9 meter, you are talking about in general. Even I can define this is also into 10 to the power minus 9 meter, or billionth of meter into 10 to the power minus 9 meter. I can tell like that. But for that reason, we should specify the range. So the range has to be 0 to 100 nanometer. Or in some cases we will get some nanomaterial properties even in less than 200 nanometer also, or more than 100 to 200 also. So it's advisable to get the definitions to write 1 to 100 nanometer or 1 to 200 nanometer. But most widely, if you want to have a major difference in the properties, then you have to mention it as 1 to 100 nanometer, or you can even call 0 to 100 nanometer. Why I am telling? Because nowadays by the facilities of electron microscopes, what we are having in transmission electron microscope, like for example of scanning electron microscope, these all we with the help of all these things we can view even in 0.1 nanometer also. So 0.5 nanometer, 0.8 nanometer, or 10 nanometer, or 15 nanometer, or 5 nanometer diameter quantum dots are available already, which has been already synthesized. I guess those who are interested in science and other stuff, so you might be knowing that the recently whatever the Nobel Prize distribution was there. So one of the prize was for the synthesis for synthesizing the quantum dots. So that is again a zero dimensional nanomaterial. So why do this particular nanotechnology has got such a huge demand in every field? Is that the reason is very simple. As you keep on reducing the size, what happens, its surface is getting exposed more and more. Okay, for example, if I take a block and cut this half, so inside the other two half these things, whatever the surface was closed, now that is exposed. Understanding? So if you are reducing this block 10 centimeter block into the 0.1 nanometer scale of one particle, each particle to 1 nanometer, then you are having, imagine the amount of surface area. So I can fit entire one to, yes, almost you can say almost a 1 acre of surface area in this particular box. So you can't even imagine how much surface area that is, right? So that is possible only with the help of nanotechnology. So that's why the nanomaterials are so different from the bulk materials. So for example, see, in civil engineering, whatever the field you take, the surface plays a very important role. The reactivity happens at surface, activity happens at surface, response happens at surface, right? Everything happens at surface. You take a chemical engineering, chemical reaction occur at surface. You take a, for example, civil engineering, the whatever the structural shape, that this everything it depends on the surface. You take mechanical engineering, again the same thing for stress and strain and wear and tear resistance, all other stuffs, hardness, everything happens on the surface. And you take, for example, biological properties or biological science, biodegradability, biocompatibility, okay, all these properties again they come under a particular on the surface itself. So that's one more thing. The next is you take, for example, of electronics, you are having the source and drain, and then in between channel material is there. This particular channel material is again, it depends on how much surface it has got, how many particles, how many surface is exposed, so that the electron might come from the source, it has to be transferred as quick as possible to the drain so that the conduction will occur. So everything happens at surface, and activity, reactivity, response, or whatever you take. Okay, so this surface is more in nanomaterials. So that is the beauty of the nanomaterial. That is the most important property of the nanomaterial, which makes nanomaterials so special compared to the bulk materials. That's why the people, that's why we can use nanomaterials in every field. Now you can ask me, how can we use nanomaterials in quantum mechanics, or quantum computations, computer science or something like that. So we are having the examples like quantum computation, supercomputers, and even nowadays whatever the supercomputers have been developed by some already highly developed countries like China and US and all. They have already have a kind of room big size now, going back to the room big size now. But the computer is not like that. But all the CPU, all other stuffs, they want to have a trillions of the task per second. They want to achieve that goal, whatever we are having in our brain. So in order to do that, they have tried a lot. Okay, but to get to their goal, if not 100%, at least for 10% to achieve that goal, so they need nanomaterials. The reason is very simple. All of you might be knowing Moore's law or Moore's law, whatever you pronounce, right? So what Moore's law says, every 18 months the number of the transistors which are sitting on a particular area of the particular chip will be doubled. So now that was the Moore, he predicted this in 1959, something like that, and he thought it will continue only for 10 to now 2 decades, but it is able to since till now it is continuing. The reason behind is that IBM, because IBM, when they developed electron microscopes, so they made it very easy so that you can understand at the atomic level and molecular level, and then you go for it. and then that was the reason we were able to achieve this particular Moore's law. We were able to continue this law, so that as every year we are getting the new cell phones or new devices which are working faster than the previous years. The reason is very simple: the more number of transistors are made to sit in that small compact space. So that it itself is telling you, as the size is reducing, the applications are getting more and more. The room size, initially what was the size of the computer? It was the room big size. And what was the memory? It was hardly 2 MB, 2.5 MB. Now what is the memory? It is in your palm, 1 TB terabyte. In a particular one cell phone you will be having 1 TB. Can you imagine? That is 1000 GB. Okay, and even forget about cell phones. You within small pen drive you can have in a number of GBs of data you can store. So this is possible. This was possible only because of the Moore's law. Mainly because of the nanotechnology, or you can say the microelectronics. Without these three things, it couldn't have been successful. So these the electron microscopes, maybe the transmission electron microscope, scanning electron microscope, or scanning tunneling microscope, for which the IBM and the scientists, they got Nobel Prize in 1986 maybe. So, and then these all things matter. So these all things play a very important role. That became a very solid background for the nanotechnology to take off, and that's how they have been used in many applications or many fields. So as I told you, for example, the nanomaterials, since because of their properties, they are very well known. So that's how, if I keep on talking, so this introduction will be too much for you guys. So I will stick on to your syllabus, and based on that your syllabus we will just try to explain. I hope you understood what exactly this particular nanotechnology is all about. So that is what matters. So the first topic is something called nanotechnology. Okay, so that's under nanotechnology. There are a lot of things to be studied. Your syllabus doesn't specifically explain whether it is just an introduction to nanotechnology, that this and all. So what I will do is I will give a brief history of the nanotechnology. I'll give you the definitions of nanotechnology, nanomaterials, nanoscience and all. Then I give you the background of the nanotechnology, and then the scope of the nanotechnology. These all things you can come under this particular nanotechnology, and according to the questions you can frame your answers. Okay, so let's start. So now before we start, so we can say that, as I was quoting in studies or previous videos, that the nanotechnology is a new technology. So I meant only for us it is a new technology, like only for students or a syllabus point of view we are talking, it's a new technology or whatever this thing is there. But when you speak about, when you think the history behind the nanotechnology, it's not actually the new technology. The technology was existing far way, like even in 400 BC or 4th century, 7th century and all, we had this technology. Okay, only after getting electron microscopes, how we found out the microbes after getting optical microscope. Similarly, we found out the nanotechnology or nanomaterials after finding the electron microscopes. That's the difference. Okay, now the thing is, how they knew that about this particular technology and all. They didn't know as such the terminology, all other these terms and all, but they used to get the applications out of it. For example, maybe the Damascus sword you take, okay, or the gold nanoparticle, the Lycurgus cup, or maybe some kind of paintings where they had recently after electron microscopes, when they saw, then only they came to know that the existence of some of the nanoparticles in it. Whereas when you speak about before the electron microscope, even though since all these things were preserved for the particular property, like Lycurgus cup was prepared for its a particular duality. That means both the lights, in the refracted light it is giving green in color, in reflected light, in transmitted light it is giving red in color. So people were amazed. So that's why they have been kept in the museum since centuries. So whenever the technological advances happens, all these people will visit, scientists will visit to the museum. Then they want to check how exactly they might have made this particular cup, or particular sword or particular painting. So then they came to then every time they failed, and then after optical microscopy also they were not able to see what are the reason for all these things. And then when the electron microscopes came, and when they were able to take off these samples, and when they weaved under electron microscope, they were able to identify the gold and silver nanoparticles, carbon nanotubes, which are present in this particular those paintings and the cups, Lycurgus cup and swords and other stuff. So what we can able to understand here, that technology was existing earlier only. That means they knew how to prepare the sword. What did they have to do? They might have taken the gold and silver and some other stuff, and they might have heated it for 1000 degrees Celsius. And if you heat it gold for 1000 degrees Celsius, definitely you are going to your gold, the bigger micro gold will not be micro gold, that will be reduced to the in particles, nanoparticles. So they will be getting a fluid kind of structure, but the nanoparticles will be present. The gold will be in nanoscale, every particles of the gold. So that's when you see the things, when you keep on reducing the size, there might be some special properties, maybe optical properties, electronic properties, magnetic properties, or maybe some mechanical properties like hardness, wear and all other stuff, wear and tear properties, or maybe the conductance properties, all other stuffs. So these all properties vary accordingly. So in order to get the best property out of it, we have to get the particular things done. Okay, so the history can be traced by the Roman period. Here, for example, we are having Democritus in 400 BAS. So in order to understand a very large, we must understand very small. So that's the tagline for our history of the nanotechnology. So we are having the Democritus, that is around 400 BC. The history that can be traced to the Roman periods, whereas the people used to use the colloidal metals were used to dye glass articles, the church articles, church glasses and all you might have seen, and fabrics also, and as a therapeutic aid in the treatment of arthritis. Even treatment of arthritis also they used to use these particular colloidal metals. Next, the purple of glaciers. So that was a popular dye, okay, in the golden days, in coloring ceramic glazes and ruby glasses. If you see the Roman era and all Roman periods, are kind of romantic kind of era. So every the whole maybe the palace or maybe anything that is coated with some colors and some kind of dyes, so in order to enhance its beautification and all. So this is consisting of colloidal. So recently, when the scientists viewed what was the reason for all this, such beautiful the appearance, the reason was the presence of colloidal gold and stannic oxide nanoparticles present in it. So, and next, the Maya blue. So Maya blue is also one of the very famous paintings that has been preserved, okay, since in museums. Okay, this is, if you trace back the Maya blue, this is actually a blue dye which is employed by the Mayas around 7th century AD, right? So that has been shown recently to consist of metal and oxide nanoparticles in addition to the indigo and silica. So the history of nanotechnology. So here the Lycurgus cup is one of the example, as I told you, a glass cup of 4th century which appears red in transmitted color light and green in reflected light. So you can see here, when I put light from above, you will get red. When I see the light from outside, you will get, it will be seen as a green cup. So can you see the difference here? It's very interesting cup. So this effect, which can be seen in the cup preserved in the British Museum in London, is due to the gold and silver nanoparticles which is present on the walls of this particular cup. So that was the reason for this particular property change. Now you can ask how the optical property is changing. Which property is changing in optical property? The reason is very simple. Again, when materials fall less than the 200 nanometer or 100 nanometer, materials exhibit very strange properties. They will not exhibit whatever the properties we are seeing in the bulk. They will not. They will somehow will have a different effect for that. The reason, there are a lot of reasons for it. So maybe the existence of discrete energy levels, whereas in bulk we are having the continuous energy level. or maybe the more surface area to compared to volume ratio. Surface area to volume ratio is very high in nano materials, whereas in bulk it is very less. Okay, maybe all these properties play into importance, and here we are having the surface plasma resonance, even that property also there. So these all properties make these particular materials to give the excellent optical and mechanical or electrical properties. So the usually here in this particular cup is actually was famous for its change in color. People thought it's some kind of magic or something like that. So no, it's pure science. So this particular particles, we were able to understand this science only after this particular thing. See, this is that's the beauty of science. You can able to some or other days we are going to prove what exactly the reason for this particular thing. So even though this particular thing we came to know that after the electron microscopes invention only. Before that we didn't know. Right. So this is the courtesy is I'm giving into the British Museum, which is traced and published in some this thing online in March 2004. So the Lycurgus cup looks green when the light shines on it, if it is in layman language, that is a refracted light, but red when the light shines inside it. Okay, when you through the inside when you give, so from inside you will get this thing. So the cup contains gold nanoparticles. So the courtesy of the British Museum. So the Maya wall painting from Cocaxtla, so that is Mexico. So here the intense blue results. See, whatever the here intense blue things are, they results from the amorphous silicate substrate with embedded metal nanoparticles. Here metal nanoparticles can be anything. Gold is a metal nanoparticle, silver is a metal nanoparticle, copper is a metal nanoparticle. So embedded metal nanoparticles and as well as oxide nanoparticles on the surface. So embedded nanoparticles in the sense inside this particular thing, and oxide nanoparticles on the surface. Okay, so that means metal nanoparticles inside the structures. Okay, whereas on the surface most probably oxide nanoparticles, maybe titanium oxide, tannic oxide, all these kind of nanoparticles. Okay, so the courtesy is here for the big courtesy is for Barbara Fash, that is Peabody Museum, Harvard University. So this is one of the these are some of the images of electron microscope where we can see the sizes of the nano particles. Like for example, metallic and oxide particles of silicon dioxide support. You can see this is the left one. Okay, you can see here the scale will be there. Here this scale is 100 nanometer. That means you can just take whatever the area which is covering here as 100 nanometer. You can take this particular thing and the same scale you put it here and you measure the particle size of this and measure the particle size of this. Like that you can keep on measuring. Okay, that is about all. Then right, we are having an atomic resolution image of the particle showing its cubo-octohedral shapes. So we are having the cubo-octohedral shapes. So this is the TEM image. So that is transmission electron microscope, which gives the three-dimensional images that we discussed in the previous video. Right. So the history continues again. So before I start any all these things from the terminology and all, so it was all credit for nanotechnology terminology. You have to give a basic credit to the Richard Feynman, who was a physicist in 1959, I guess, right? Somewhere here, I guess I mentioned. Yes, in 1959, in his famous talk, he has told there is plenty of room at the bottom. That means he wanted to guide every student, every scientist or every scientific community to work at atomic and molecular scale. Then he gave two challenges also that we will discuss later. From then in 1959, the scientific community started working and concentrating at molecular and atomic level. So what is the size of the molecules? We are having 10 to the power minus 8. What is the size of the atom? It is around 10 to the power minus 11 to 12. So what is nano? It is 10 to the power minus 9. So this nanotechnology or nanomaterials falls under the in between the atomic and molecular size. Understanding? So So that's how the nanotechnology came into existence. For example, nanomaterials came into existence, or else the before like when the scientist, if the scientist was were not concentrated at atomic and molecular level back in that time, definitely someone would have done it, but it would have taken much more time or maybe decades. But because of the Richard Feynman's insights, okay, the whole scientific community started working towards it, and that's how that itself becomes a very background for this particular nanotechnology. But terminology point of view, in the early, ultrafine technology, that this kind of these things were there earlier, but when exactly they got the name nanotechnology? In 1974, Japanese scientist Nario Taniguchi, so he was the first one to use the term nanotechnology for the first time. So he called the term nanotechnology. So he said that if any materials are falling in 0 to 100 nanometer or 200 nanometer, we can consider them as a nanomaterials, and any science or any technology or any exploitation of the properties of these nanomaterials in order to gain some applications, then that will be called as nanotechnology. That's what he defined. Okay, so that's how he gave the term nanotechnology. Okay, so since why we need a new technology, new term for the nanotechnology? Already we have a technology. Why separate nanotechnology? The reason is very simple. As I explained you earlier on the previous classes, nanomaterials behave very strangely compared to the bulk materials. They do not exhibit the same property what we see in the bulk. If, for example, if the gold color is yellow in the bulk, but if you reduce to the 80 or 50 or 80 nanometer, I am getting purple color. Around 50 nanometer or 30 nanometer, I am getting red in color. Can you imagine? So optical properties are not same as in bulk. So that's the difference. That's why we are having the whatever the things were preserved. That's why we are having the nanoparticles in them. That's why they are special. That's why they have been preserved, right? So that's why we need to have a separate technology or separate branch of science. He thought, so he called the term nanotechnology. So in 1981, IBM develops the first electron microscope. The scanning tunneling microscope by the Gerd Binning and Henrik Rohrer at IBM Zurich Research Laboratory, for which they were awarded a Nobel Prize in Physics in 1986. The first commercially available atomic force microscope was also introduced by the same team in same company in 1989. So 1981 they got STM, that is scanning tunneling microscope. They got Nobel Prize for this. Even though we are having a couple of electron microscope, they went for the Nobel Prize they got it for only STM. The reason is very simple. Scanning tunneling microscope, you can scan and see the two-dimensional morphology, and in TEM you can see the three-dimensional morphology of nanoparticles. We are having AFM, we are having many other electron microscopes, but they chose STM for Nobel Prize, which is the reason behind that is the scanning tunneling microscope. They have something speciality on their tip of the microscope. Tip of the microscope is designed in such a way that a single atom can be picked and it can be replaced with some other place, or it can be placed on some other place. With the help of this only, they were able to create the IBM logo that will come to later. So that's what happened in 1974 and 1981 STM, and 1986 they got a Nobel Prize. 1989 again they did AFM. So in 1985 the buckyball, so that the scientist at Rice University and University of Sussex, they discovered the C60, Richard Smalley and Rupert Curl, so for the Rice University, and Sir Harry Kroto, University of Sussex, they discovered the C60 carbon materials or the ball. So they called it as C60 because 60 carbon atoms were there in this particular material, and buckyball they called because it looked like a buckyball and Buckster fullerene, what we call, because it contains the hexagonal structure followed by the pentagonal kind of structure, kind of a football this thing, which is a little bit bucky, so that's why the buckyball they said. So they gave that was in 1985. So that played a very important role, because after C60 then the people started, the scientific community, they started coming up with the new buckyballs and new what is it, fullerene materials and carbon based materials. So that opened up new field in material science. In 1986, the Engines of Creation, that was the first book which was on the nanotechnology by the Eric Drexler, which was first book which has been written, that is Engines of Creations on Nanotechnology by Eric Drexler. So atomic force microscope was invented by Pinning, C. Quat and Seeger. Okay, so that was AFM. Okay, and IBM logo was made by using individual atoms. That's what you can see here. Every small atoms are there here, and IBM logo was made with the help of this particular and the carbon nanotubes was discovered by again Japanese scientist. He discovered the carbon nanomaterials or carbon nanotubes, and that was the biggest invention in nanomaterials, because the carbon nanomaterials has got something very specific even among nanomaterials. It's very simple, because see, the carbon nanomaterials are nothing but the materials whose one of the diameter is at nanoscale, but carbon nanotube is nothing but its one dimension is free to move, its thickness and the diameter is in the scale of nano. So here what happens in carbon nanotube, why it is so special, is that carbon nanotubes has got three different structures. We have got chiral, zigzag and armchair. So if I want particular conductivity, all these three structure will give you the particular properties, all three electronic properties. If I want a carbon nanotube to be a conductor, I can make it. If I want to make the carbon nanomaterials to be a semiconductor, yes, I can make it. If I want to make carbon nanomaterials to be an insulator, that also we can make. So that's the beauty of the carbon nanotube. And also, so far from the beginning of the world till now, the highest conductive material on earth is carbon nanotube, and highest thermal conductive material on earth is carbon nanotube so far. And these carbon nanotubes are simply made by rolling the graphene sheets, again the two-dimensional nanomaterial, okay, which is the stiffest material on earth now. Why all these properties are high or extreme at nanoscale is that we know that the diamond is so strong, right? And we know that what are the bonding, what is the bonding in the diamond? It is carbon covalent bond, sp2 sp3 hybridization. The similar bondings you are seeing it here in carbon nanotubes and graphenes. So that's the reason why the nanomaterials are becoming more and more giving the very excellent and very strange properties than the bulk materials, and which are happen to be very useful. In 1999, nanomedicine, there was a first book on the nanomedicine and to the medical field was written by the R. Freitas. So this comes like an outline or a outline of the history. So let's begin the terminology. Now, what is the definition of this thing? What is nanotechnology, and what is nanomaterials, nanoscience, nanotechnology, background? All these things we will discuss in the next class. So that was the history of the nanotechnology. In next class we will discuss about something else.